So now we're going to go through a few examples so that you can evaluate how to use the energy equation for understanding steps and sills. In your first example, you are given a rectangular channel with a bottom width of 10 feet and a flow rate of 500 CFS. The channel still at the step is relatively horizontal, with an upstream flow depth of 6 feet and a step height of 2.5 feet. I would like you to determine the depth of the step, but you also need to verify that the upstream depth of 6 feet is accurate. So the governing equation is the specific energy at point 1 is equal to the specific energy at point 2 plus delta Z. The solution tells us that the energy at point 1 is equal to the depth, 6 feet, plus the velocity squared, which is 500 CFS, divided by 10 times 6, divided by 2 times 32.2 for the gravity, and you're given 7.08 feet. Now the energy at point 2 will be the energy at point 1, 7.08, minus the height of the step, which is 2.5. So our energy at point 2 needs to be 4.58. Now we need to verify that E2 is greater than E min. So we need to calculate the DC and the E min. Remember, to do this, the Froude number is equal to 1. If we set the Froude number equal to 1, you can rearrange the Froude number equation to tell you that the critical depth for a rectangular channel is equal to the cube root of the flow rate squared divided by the base width squared times gravity. The flow rate is 500, the base width is 10, and the gravity is 32.2. We're given a depth of 4.27. Once we know the critical depth, we can find the minimum energy. The minimum energy is the critical depth, 4.27, plus the flow rate, 500, divided by 10 times 4.27 squared, divided by 2 times 32.2. This will give us a minimum energy of 6.38. Oh no, E min is greater than E2. What this means is your flow is choked and backwater will occur. So to continue, since the flow is choked, the D1 provided is not accurate and the water will backwater. So we are going to set D2 equal to DC, which is 4.27 feet. And the energy at point 2 will be equal to the minimum energy, which is 6.39 feet. We now solve for E1 as the energy at point 2 plus the step height, 6.39 plus 2.5. This gives us an energy at point 1 of 8.89. We set the energy at point 1 equal to the depth plus the velocity head. We rearrange the equation and we determine that we have D1 cubed minus 8.89 D1 squared plus 38.8. Note that our channel is subcritical and D1 must be greater than 4.27 and D1 must be greater than 6 feet. So we can put this into Excel and use goal seek, making sure that our depth is greater than 6 feet. And we will get a depth of 8.23 feet. So you can see from this example, our depth, which we thought was 6 feet, is actually 8.23 feet. And the critical depth, or the depth at the step, is 4.27. Let's try another example. In this example, we still have the same channel with the same flow rate and base width. It's relatively horizontal. The upstream depth is 2 feet, but I want to know what the maximum height is. So remember our governing equation. The energy at point 1 is equal to the energy at point 2 plus delta Z. Note that the maximum step will occur when the flow depth of the step is critical depth. So D2 is equal to DC, and E2 is equal to E min. And from the prior example, we determined that DC was 4.27 feet, and the minimum energy was 6.39 feet. Since D1 is less than the critical depth, we know the flow this time is supercritical. We're going to calculate the energy at point 1, D1 plus V1 squared divided by 2G. and we get a specific energy of 11.67 feet. We can subtract the energy at 1 from the energy at 2, and we'll get a step height of 5.28 feet. So the maximum step height for this example is 5.28 feet. Now let's try an example with a sediment sill. You're given the same rectangular channel, 10 feet, 500 CFS, but this time I want to put a sill in. The flow depth is 6 feet upstream and the sill depth is 2 feet. So the governing equation tells us E1 is equal to E2 minus delta Z. We know from the previous example that E1 was 7.08 feet. We also know that the flow was subcritical. E2 is equal to E1 plus delta Z, and since delta Z is 2 feet, our energy at point 2 has to be 9.08. Since we have a sill, the energy at point 2 is much larger than the energy at point 1. We set the energy at point 1 to the depth plus the velocity head at point 2. We rearrange the equation and plug in the constants, and we get the depth at point 2 cubed minus 9.08 times d squared at point 2 plus 38.8. We use goal seek, and we will get a depth of point 2 of 8.55 feet. Realizing, remember, it was subcritical flow, so our depth will be greater than 6 feet. I hope these examples have helped better illustrate to you how critical depth is an important concept in steps and sills, how energy, specific energy to be accurate, helps in calculating depths, step heights within channels.